Grok 4, this is the smartest AI in the world. It really is remarkable to see the advancement of artificial intelligence, how quickly it is evolving.
When Google finished testing their most powerful quantum chip, the results were so extreme that no one in the lab could explain them. So they did what any team would do. They fed every byte of data into Grok 4 and asked it to make sense of what happened. But Grok 4 didn't optimize. It didn't suggest improvements. Instead, it flagged something buried in the numbers that the entire research team had missed. A pattern that, according to Dr. Hartmut Neven, head of Google Quantum AI, shouldn't exist under any model we currently use.
You just say that if you took every molecule in the universe and converted it into computing power, that this thing has more computational power than the universe if it was a computer?
When Neven read the full analysis, he went quiet. Those present say he stared at the screen, set down his coffee, and didn't speak for nearly a minute. What Grok 4 discovered didn't just challenge a theory, it raised a question about reality itself, that no one, not the engineers, not the physicists, not even Grok, could answer. That question is what this video is about. The wall. Here's the deal. Every computer on the planet, every phone, every supercomputer runs on the same ancient trick. Billions of tiny switches flipping between 0 and 1, billions of times per second. That's it. Every photo, every bank transfer, every movie you've ever streamed, brute force switching. Engineers have spent decades shrinking these switches down to 2 nanometers, just a few atoms wide. But here's the problem. No matter how small or fast they get, classical computers still solve problems one step at a time, one possibility after another, no shortcuts. And at the atomic scale, the physics that makes it all work starts breaking down. Heat, noise, quantum interference. The architecture has a death sentence. But what if I told you someone built a machine that doesn't just push past that wall, it ignores it entirely? The chip that shouldn't exist. Google's Willow processor doesn't work like anything before it. Julian Kelly, the lead engineer on Willow, spent years building toward this moment, and even he wasn't ready. Willow doesn't use transistors. It uses qubits, quantum bits that can be 0, 1, or both at the same time through a property called superposition. When qubits interact, they become entangled. What happens to one instantly affects the others. They don't solve problems step by step. They explore massive possibilities all at once. Now, pay attention to this. Willow has 105 superconducting transmon qubits cooled to near absolute zero. In every quantum system before this, adding more qubits made the system less stable. More components, more noise, more errors. That was the rule. Willow broke it. As more qubits were added, errors went down. Not sideways, down. It crossed a threshold in error correction that physicists had chased for 2 decades. Here's where it gets wild. To see what Willow could actually do, the team ran a benchmark called random circuit sampling. You don't need the math. What you need to know is this problem would take the most powerful classical supercomputer longer than the age of the universe to solve. Not 1,000 years, not 1,000,000. Longer than the 13.8 billion years since the Big Bang. Longer than the time for every star to burn out and every atom to decay. The answer still wouldn't be finished. Willow solved it in under 5 minutes. Kelly later said he checked the result 3 times before he believed the readout. A chip smaller than a fingernail had just completed a computation that exceeds the entire lifespan of the observable universe. Not by a small margin, by a gap so vast that human language doesn't have a clean way to describe it. And here's the catch. Willow wasn't struggling. There was no instability, no sign it was being pushed to its edge. As the system scaled up, it got more reliable, more stable, more controlled. Dr. Neven, reviewing the benchmarks, reportedly described it as the most unsettling result he had ever seen in 30 years of research. Because machines don't do this. Errors are supposed to pile up. Noise is supposed to win. Willow did the opposite, and nobody could cleanly explain why. If this is already making you rethink everything you thought you knew, hit subscribe, because what Grok found next is going to keep you up at night. The question nobody asked after the results were verified, the next step seemed routine. Feed Willow's data into an analytical system. Let it find patterns, flag anomalies, suggest optimizations. Grok 4 was given the raw numbers, internal logs, and every supporting measurement. Its job: compare, contextualize, clarify. And this is where everything changes. Instead of suggesting ways to make Willow faster, Grok 4 locked onto something no one had flagged. It didn't ask how the system could perform better. Dr. Sergio Boicho, Google's chief quantum computing theorist, said the AI reframed the entire problem, questioned the assumptions behind the analysis, and noticed that standard tools might not describe what was happening inside Willow. And the question it raised was devastating in its simplicity. If a system completes a task that, according to everything we know about physics, cannot be completed within the physical limits of the observable universe, then where did the computation actually happen? Read that again. If the work couldn't fit inside the time and energy constraints of our universe, what space was doing the processing? Dr. Boiso later described the moment he read Grok's output as, "The first time a machine made me feel like I was the one who didn't understand the question." Grok 4 didn't answer it. It didn't propose a theory or claim to have cracked anything. What it did was worse. It pointed out that every researcher had been assuming, without realizing it, that the computation happened entirely within our universe. The data didn't support that assumption, and that's when the mood in the room changed. This wasn't about a fast chip anymore. Something fundamental didn't line up. The closer people looked, the harder it became to dismiss the feeling that they were staring at something that wasn't supposed to be possible. But what Grok flagged next made the original question look simple. The pattern that can't be explained. Here's something anyone in quantum physics will tell you. Quantum systems are fragile, brutally fragile. Coherence fades fast, outside noise shreds quantum states. And as systems grow larger, they get worse. Every added component is another crack. For years, this shaped every decision in the field. Bigger meant riskier. Scale meant chaos. The goal was never stopping mistakes. It was delaying them long enough to do something useful. And get this, that's not what Willow's data showed. As the system grew more complex, instability didn't increase. It decreased, not randomly, not in messy fits and starts. The improvement followed a structured, almost deliberate rhythm. The background noise that defines every fragile quantum system wasn't acting like noise anymore. It was organizing. Dr. John Preskill, the Caltech physicist who coined the term quantum supremacy, reviewed the data and noted the error suppression went beyond standard predictions. Grok 4 flagged the same thing. The system didn't just handle scale, it thrived on it. Order appeared where randomness should have dominated. Now, here's what made even the optimists uncomfortable. In quantum systems, coordination between qubits happens through entanglement. That's expected. But the stability Grok flagged seemed to arise from connections that the engineering team didn't believe they were directly controlling. Something was keeping the system coherent beyond what the blueprints accounted for. This didn't break any known laws of physics. It found tiny gaps between them, and that made it almost impossible to wave away. The explanations people reached for next only made things stranger. Two realities, both terrifying. When results push past existing models, science has limited moves. Tighten the equations, expand the framework, or confront the possibility that the framework itself is incomplete. That's the cliff everyone was standing on. Two main explanations emerged. Neither one is comforting. The first comes from physicist David Deutsch at Oxford, a founding architect of quantum computing and lifelong advocate of the many worlds interpretation. In Deutsch's view, quantum processes don't happen in one universe. They happen across many coexisting realities. Every possible outcome exists simultaneously. Reality doesn't choose one result, it splits. Under this framework, Willow didn't test possibilities one by one. It occupied all of them at once. The staggering output didn't come from inside a single universe. It was spread across countless versions of reality. Deutsch has argued for decades that quantum computers would be the first experimental evidence for this. After Willow's results, he described them as entirely consistent with computation distributed across the multiverse. But here's the deal. The second explanation avoids parallel worlds and introduces a different strangeness. Researchers in quantum gravity and information theory suggest reality itself may contain deeper computational layers. Not separate universes, but buried architecture within this one that our physics doesn't describe. Willow didn't borrow power from somewhere else. It accessed parts of our own reality we don't yet know how to observe. The computation happened here, just not in any space we can currently map. Think of it this way. Imagine a calculator that gives you answers too large to fit on its screen. One explanation says, the calculator is spreading the work across many invisible screens you can't see. The other says the calculator is using parts of its own screen you never knew existed. Both sound impossible. Both explain the same result. Either reality splits in ways we cannot detect, or it contains hidden depths we've barely begun to explore. Grok 4 didn't choose between them. Both were internally consistent. Both matched the data. What mattered wasn't which was true. It was that reality itself had become the open question. Before this, reality was the stage, fixed, predictable. Now it was the mystery. And when that happens, the questions stop being technical. They become existential. What this unleashes. Once you stop focusing on the machine and start thinking about reality itself, the implications hit fast. If systems like Willow can handle complexity that was once unreachable, entire fields transform. Medicine stops relying on rough molecular approximations. Climate science moves beyond simplified projections into deep pattern recognition. Problems labeled too complex don't disappear. They become solvable because the tools addressing them operate on a fundamentally different level. But here's the catch. Every leap in capability drags a matching risk. Modern encryption, keeping your bank account, medical, records, and private messages safe, works because certain math problems are too hard to crack. Dr. Michelle Mosca, a cryptography researcher at the University of Waterloo, has warned that powerful quantum systems could break widely used encryption far sooner than governments are prepared for. That timeline just accelerated. And there's a quieter danger. When AI works alongside machines that solve problems beyond human comprehension, it produces answers people cannot fully verify or challenge. We enter a world where solutions exist, but understanding doesn't. The gap between knowing and comprehending keeps growing. Nobody has a plan for that. What comes next isn't a technical problem. It's a human one. Grok 4's final word. When Grok 4 was presented with several competing interpretations and asked to choose one, it refused. Not because it was confused, because the question didn't fit the data. Whether the computation happened across parallel realities or within hidden. Structures of this one didn't change the practical result. A boundary had been crossed. Humans had built something that didn't just stretch existing explanations, it revealed exactly where those explanations stopped working. The machine didn't break any rules. It showed us the edges of the rulebook. Dr. Neven, reflecting on the full arc of Willow and Grok's analysis, put it simply. He said we keep assuming nature computes the way we do, step by step, inside a single frame. Maybe the most important thing Willow revealed is that nature doesn't share that limitation. We do. Grok 4 didn't issue warnings or predict disasters. It did something harder to shake off. It reflected the situation back exactly as it was, without drama, without comfort. Here is what the data shows. Here is where explanations thin. Here is the gap. Google's quantum AI division is already designing Willow's successor with significantly more qubits, explicitly to test whether the anomalies Grok flagged hold at larger scales. If they do, the implications won't stay in physics labs. For all of human history, we believe there was one reality, the one we could see, touch, and measure. Now, the machines we built are telling us otherwise. So, here's the question I can't stop thinking about, and I don't think you'll be able to either. What happens when the tools we created know more about the universe than we do? Do we follow them into the unknown? Or do we admit we're not ready? Drop your answer in the comments. And if this one got under your skin, subscribe, because the next video goes even deeper into what's being built behind closed doors, and you don't want to miss it. I'll see you there.